Dear attendees of the 6th International Symposium on Visualization in Joining and Welding Science through Advanced Measurements and Simulation. I very much appreciate that Professor Tsukamoto, as the conference chair, and the program committee member, Professor Kirihara, invited me to give this plenary talk. Unfortunately, I cannot be with you today personally, but Professor Kirihara and Professor Tsukamoto accepted that I send you a video recorded message. And video recording, by the way, is the right keyword also for my presentation today, which is titled Seeing is Believing, Some New Insight into Laser Beam Welding and Cutting Processes. And you might imagine this seeing is realized by a high-speed video recording. The motivation is clear. We want to understand the process, the sub-processes, all the details. We want to understand why the processing result is as it is. And by understanding the transformation and transport phenomena in detail, we are able to improve efficiency and quality. We get the process under control. The task is to identify the dynamics of the transformation processes, melting, vaporization, of the resolidification, of the geometries of the phase boundaries and the free surfaces, and of the flow conditions of the melt and perhaps, if happening, also the vapor. Today we have excellent high-speed video cameras with very good temporal and spatial resolution so that we can see very detailed the temporal behavior in a rather excellent slow motion, and also the spatial distribution of the different details of the interaction zone. So we have very good tools and we should use them. Before I continue with the work of my group, I have to mention three leading figures in this field, which are Professor Arata, Professor Matsunaga, and Professor Katayama, all of them being or having been with the JWRI, with the Joining and Welding Research Institute in Osaka. And obviously this makes clear that it does make sense that this conference with this topic is located in Osaka and organized by this institute. A short introduction also, what will you see today in this presentation? I will concentrate on 4 examples of work we did some years ago, partly many years ago, and very recently. And the 4 topics, 2 of them are about cutting processes, and 2 of them are about welding processes. I would like to introduce the trim cut or also edge cut technique with 2 historical examples. First, on the left side, a result published by Professor Arata, mentioned already earlier, in 1979, when he investigated the laser beam oxygen cutting process of mild steel and revealed cyclic process behavior, namely the heating of the cutting front up to the ignition temperature, then ignition of the process, exothermal reaction, which is after a certain short period even accelerating the burning front to a higher speed than the cutting speed, so the burning front is running out of the laser area. Then the heating of the laser does not occurring anymore, so the burning front extinguishes and the laser is catching up the front and ignites a new burning process with the related exothermal reaction, and so on. A cyclic process is occurring, and explaining the rough and periodic striation structure of certain laser oxygen cutting processes. In this case, the view onto the cutting front was for the first time made possible by cutting along the edge of a sheet. By this, the cutting front is accessible. Nearly 14 years later, my group picked up the idea of Professor Arata and added a certain detail to this technique, namely using a transparent glass sheet as a replacement of the missing cutting flank, so that the gas jet is working in a more proper way comparable to the real cutting process. And by this, we could investigate the striation formation during laser beam fusion cutting for the first time. Further, 12 years later, in 2005, it was the time when the multi-kilowatt fiber laser cutting systems came up. Also, the camera equipment improved regarding the capabilities of spatial and temporal resolution. So we could even make colored high-speed videos of the CO2 laser cuts in comparison to fiber laser cuts. And by that, we could demonstrate that earlier theoretical predictions with our simulations were confirmed with these high-speed videos, where we see that we have on the left side a very smooth, regular flow of the melt on the cutting front, only a little bit breathing, but not as on the right side with the fiber laser stumbling with the irregular flow due to the irregular absorption distribution within the curve with a 1 micron radiation. And this is explainable with multiple reflections. We and also our customers recognized more and more the value of the trim cut technique as an important source of information about the process. So we built up an automated test bench for trim cut experiments where the workpiece and the window are movable, motorized, and the movement and the positioning is programmable. This is very much improving the efficiency of these kind of investigations. Another important method to analyze the dynamics, or an additional important method, is the so-called streak imaging technique, where line-shaped regions of interests are put together on the time axis in a row, and by this hot spots on the cutting front on the interaction zone, moving from the top to the bottom, are visible as lines in the streak image. And the inclination of the line is giving us a clear indication about the speed of these moving spots. Here we see two important geometrical parameters of a trim cut setup, namely the trim cut width and the replacement flank distance. For example, here in setup B, we have a situation which is quite near to the real cutting process with a reflecting glass plate, allowing also multiple reflections near to the process. And in this case, we are far away from a realistic process because the flank formed by the glass plate is far away from the cutting process, so no multiple reflections are supported by this setup. And this is used to switch multiple reflection on and off for the investigation described in the next slide. And indeed, with the setup B, the cross-section and the side view of the resulting cut flank is very similar to the real cut situation, whereas with the setup C, we have a much more inclined flank, less material removal due to missing multiple reflection, but we have a much higher quality also. The cut flank is not as rough as in these cases. The striations are really nearly straight and very fine. Moreover, we see the effect of the multiple reflection in the case B by the wider molten zone behind the laser region, whereas in the case C, the solidification occurs much earlier and there is no heating of the melt behind the laser. In this section, I will address some aspects of different perspectives to be used for the videography of the laser beam cutting process. For example, on the left side, we have the inclined bird's eye view, which obviously provides a very instructive perspective. On the other hand, it requires an untypically high nozzle distance and a wide curve to access the interaction zone. On the right side, we see the coaxial view through focusing optics. This enables inline process monitoring, but on the other hand, provides only a very restricted image quality. What is also very important is the combination of visualization and simulation. The videography can check the validity of the simulation tools, and on the other hand, the simulation tools can support the video interpretation by giving additional information, for example, about the temperature distribution or the heat flow distribution. We just discussed the pros and cons of this inclined view into the cutting front. If we want to have a look at the melt ejection, the distribution and the speed of the melt ejection, and to get accurate values for this, to investigate the correlation with the resulting Burr attachment, we need two perspectives. One look or view into the curve from behind, and one look from the side. Here you see a sketch of the used setup with two photron cameras observing a process in 6mm stainless steel. It is very instructive to look at the melt ejection pattern for different speeds and powers. In this case, the melt ejection pattern is time averaged over 10,000 frames. What we, for example, see is a long melt drag leading to a long burr, and a very unique pattern in the case of the best quality with the smallest burr. This is a synchronous representation of the high-speed videos from both perspectives. And here we do not only see the side view, but also the front view from behind into the cutting curve. And below the sheet, we see that this melt jet is in fact a combination of two melt jets behind the cutting front. The so-called swallow-tailed melt ejection, which cutting experts know quite well, and they also know that this is a good configuration for getting dross-free cuts. However, here we see the temporal behavior. We see the speeds of the speed distribution of the melt ejection, and we also see that there is a liquid sheet between the front and the back side of the melt flow, which is connecting the central melt ejection at the front and the swallow-tailed melt ejection dragging behind that. In any case, it is obvious that this pattern is giving the lowest value for the burr height, and by this is recommendable to be selected for process optimization. The synergetic effects of a hybrid welding process combining a deep penetration welding laser with a filler material providing and heat providing gas metal arc are well known. These kind of processes are in industrial applications since about 20 years. We can, by this, increase the speed. We can bridge gaps between sheets in a butt joint configuration. We can level misalignments of thick plates, and we can get very high quality in thicker section stainless steel. In laser arc hybrid welding, the interactions of the laser beam, the arc, the droplet transfer, the vapor plume, and the vapor capillary, as well as the effects on the stability of the melt pool itself, are rather complex. And during our continuous further development of laser arc hybrid welding processes, we asked ourselves, shouldn't a pulsed arc be combined with an appropriately modulated laser beam? Isn't it much more natural also to modulate the beam adapted to the pulsed arc instead of using simply a continuous wave laser? The success of the work based on the idea of modulation control in laser hybrid welding was essentially supported by comprehensive high-speed video diagnostics. Only with this we were able to get a better insight into the influence on the geometry of the melt cavity, of the droplet transfer, the keyhole behavior, and the thermal cycles of the droplet transfer and the keyhole opening, and also about the mutual interactions of these different sub-processes. A schematic diagram of the laser modulation control depicts the main components and their connections. We are using a master-slave configuration. The master is formed by the arc closed loop, which is provided by every modern arc source anyway. This is working based on certain characteristics of the current or the voltage of the arc. Then we use a current transducer to get a trigger signal for controlling the laser source modulation. First of all, we have to set the trigger level, slope, and delay. We detect the trigger and set the laser modulation parameters accordingly. And according to this setting, the signal for the laser modulation is put out. And then the laser source and the arc together act in the combined hybrid welding process. During the investigations, we found out the following. The best arrival position of the droplet transfer is the leading edge of the vapor capillary. As soon as the droplet arrives, the laser modulation level has to be increased to support the entering of the droplet into the capillary. After that, the laser power level is reduced again, the capillary is narrowing and waiting for the next droplet. And this is repeated in a regular cycle. The result is convincing. No underfill or undercut, but a flat seam surface. No sagging or drop through, but a sound and regular root formation. So there are three main measures to be taken. First of all, the droplet travel time after arc ignition has to be identified and adjusted properly. The droplet arrival point on the weld has to be appropriately selected, namely near to the leading edge of the vapor capillary, and the keyhole cycle has to be adapted by controlling it with a laser modulation. Thus, we can achieve three important effects. First of all, by the modulation, the heat input is reduced and this avoids drop through. The breathing of the keyhole, due to the periodic modulation of the laser, enables a stable droplet intake and, what is even more exciting, a deep penetration of the filler material into the plate. From my point of view, the most exciting visualization technique for looking into the interaction zone of laser processes is the so-called X-ray phase contrast imaging. We are using synchrotron radiation at the German electron synchrotron in Hamburg, together with colleagues from the RWTH Aachen University, from the chair for laser technology over there, and with colleagues from the laser institutes in Stuttgart and Erlangen. The experimental campaign is funded by the German Research Foundation, and we are doing these experiments since last year and will continue this in the next years 2 times a year. The synchrotron radiation is coupled out of the accelerator ring in so-called beamlines, and along these beamlines there are so-called experimental hutches, which are providing the laboratory space for these kind of experiments. The setup is quite simple in principle. The very bright and coherent synchrotron X-ray beam is transmitted to a narrow sample in the area of the laser material interaction, and the transmitted light is then passing a scintillator where the X-ray radiation is transformed into visible radiation, and this is then captured by a high-speed video camera. The phase contrast imaging technique does not only make use of the attenuation of the radiation when passing through the object, but it also makes use of the different phase shift of the radiation depending on whether the material is fluid or solid. This is the reason why we can identify very clearly also the phase boundary between the molten and the solid state. And by this we get beautiful images of the process, not only seeing the vapor capillary and the birth of bubbles within the melt pool by the reflected laser light forming a cavity which is supported by increasing vapor pressure due to narrowing of the entrance of the vapor capillary. We also see the movement and the dynamics of the melt line itself. By evaluating the gray levels of the capillary images, under certain assumptions regarding the symmetry of the capillary, we can reconstruct its three-dimensional geometry. And having this, we can use ray tracing calculations to simulate the distribution of the absorbed laser intensity on the keyhole wall, here depicted for 3 different speeds. Also, the interaction zone of the laser beam cutting process can be visualized. Here we see the cutting fronts of a static laser beam and laser beams oscillating in cutting direction with increasing amplitude from the left to the right. It can be recognized that with increasing amplitude, also the cutting front is expanding accordingly. The evaluation of the dynamics of these kind of cutting processes is still in progress and will be published in the near future. I come to the conclusion. First of all, our mission is to gain not only know-how, but to proceed to the target, also to gain know-why. And for this, visualization and interpretation is the key. We also found out 3 key measures. First of all, achieving accessibility. You remember the example with the trim cut technique, and of course the recent investigations using X-ray phase contrast imaging. Another point is the combination of perspectives. Perhaps you remember the example with the melt ejection and its correlation with the burr formation. We used 2 orthogonal perspectives in order to get the complete picture of this 3-dimensional situation. One perspective would not have been enough to get the complete picture. And last but not least, deriving appropriate modulation methods. From our point of view, modulation can help to build up stable and efficient processing cycles instead of simply using continuous wave radiation and let the process run by itself without control. And this also leads me to the small outlook. Modulation can even support the process stability and the controllability if it is done only with a very small amplitude. We call it minimally invasive laser modulation. With this kind of modulation, we get interpretable process response signals without disturbing the process. And these signal patterns are ideally suited for closed-loop control with artificial intelligence. With this outlook, I thank you very much for your attention, and I wish you very inspiring experiences during the next 2 days. Thank you very much.